Hello everyone. Today we are going to start this second chapter of module 2, that is stoichiometry of cell growth and product formation. So, first we will quickly revisit the last discussion. So, we started with material balance. So, for this we discussed we need to have the flow diagram and all the assumptions need to be clearly made, and then we apply law of conservation of mass. So, it says in minus out plus generation minus consumption equals to accumulation. So, that is the mass balance equation. To apply this, we further require the stoichiometric equation. So, for that we discuss how this carbon source, oxygen, nitrogen source is converted to biomass, water and carbon dioxide, and further there can be another metabolite, that is your product. Then further we discuss how to calculate the yield coefficient. So, yield is defined as y, and if it says yx by s means delta biomass form per gram of substrate consumed. Similarly, if I say yp by s, so this will be amount of product formed divided by per gram of substrate utilized. And when you want to start this stoichiometry relation, we need to know the general formula for biomass. So, that is what we discussed in the last lecture, that 4 major elements: carbon, hydrogen, oxygen and nitrogen constitute about 90 to 95% of biomass. So, today's lecture, as I discussed yesterday, that when you are going to do this mass balance, you are having few unknowns. For example, here A, B, C, D and E, there are 5 unknowns. To solve these 5 unknowns, you require 5 equations. And how you got the 5 equations? That was carbon balance, hydrogen balance, oxygen balance, nitrogen balance and respiratory quotient. Now, what we discuss further, that measuring the amount of change in the water molecule, it is not very significant, because most of the time in bioprocess we deal with the aqueous environment. The synthesis of water molecule, it is difficult to measure precisely. So, we require some another equation to find these unknowns. So, for this one option is to go for the electron balance. The electron balance, it says the available electron, it refers to the available electron electrons which can be transported to oxygen on combustion. So, based on this electron balance, now we will again try to do the elemental balance, and based on this we will predict theoretical yield. So, to start with, let us define that what is degree of reduction. The degree of reduction is defined as number of equivalent of available electron. This equivalent we say based on the carbon atom in a material, and this material can be your biomass, it can be carbon source, it can be nitrogen source per gram atom of carbon. That is why we are calling as a equivalent. Now, how to proceed with this? So, we consider the balance of each atom in the electron balance. For example, we consider plus 4 for carbon. So, for the carbon we are considering plus 4, hydrogen we consider plus 1, oxygen we consider minus 2, nitrogen we consider minus 3, phosphorus we consider plus 5, and sulfur we consider plus 6. Now, it is very interesting to know here these available electrons are conserved during the metabolism. It means one can apply the electron balance as well as a part of material balance, because available electrons are conserved starting from the substrate to the product. Now, let us say this is your typical formula for a substrate CWHXOYNZ. So, first we have to calculate the number of available electrons. How we will proceed? For the carbon, valence for the carbon is plus 4. So, this will be 4W. For hydrogen plus 1, this will be 1X. Oxygen minus 2, so this will be minus 2Y, and nitrogen minus 3, so this will be minus 3Z. Once we sum it up, then we have to calculate per gram of carbon atom. How many carbon atoms are here? It is W. So, we have to divide this sum with the W, and this gives the degree of reduction which is written as gamma. So, gamma is degree of reduction. If I write S, degree of reduction of substrate. If I write B, degree of reduction of biomass. If I write P, it means degree of reduction of product. Further, it is also interesting to see if I calculate degree of reduction of carbon dioxide. This will be 4 minus 4 0. For water, this will be 2 minus 2 0. Ammonia 3 minus 3 plus 3 0. So, degree of reduction of these compounds are 0. So, once this is 0, it means when we are going to do this calculate the stoichiometry coefficient, so these term will not appear there. So, for example, if you see here, so if I do this electron balance, so for this is 0, CO2 is 0. Now, let us see how we proceed here. So, this is your substrate, this is aerobic process we are considering. So, we are giving oxygen, this is a nitrogen source, and the end product is your biomass, water, carbon dioxide, and this is another metabolite is your product. Metabolite. Now, we have unknowns A, B, C, D, E and F. These are the unknowns. Now, from this stoichiometric coefficient, if I ask can you calculate the Yp by S, Ybp by S, then what is the stoichiometric coefficient of product? F into molecular weight of product divided by molecular weight of substrate, because here stoichiometric coefficient is 1, weight of substrate. Now, for the same stoichiometry relation, if I do this electron balance. So, before proceeding for electron balance, as I told we have to calculate the degree of reduction. So, here there will be degree of reduction of your, here you are going to have gamma substrate, you are going to have gamma of biomass and gamma of the product, alright. So, once we know this degree of reduction, now let us apply. So, this will be gamma S into carbon stoichiometry is W. So, this will be W into, this will be W into gamma Yes. Next is oxygen. Oxygen is -2. So, O2 will be -4 A. This equals to, for nitrogen source we are considering ammonia. So, this degree of reduction is 0. For biomass this will be C into degree of reduction of biomass. So, this will be C gamma B. For water degree of reduction is 0, carbon dioxide degree of reduction is 0, and for the product degree of reduction is gamma P. So, this will be plus F J gamma P. So, from this equation it is also possible to calculate the oxygen demand. What is the value of stoichiometry coefficient of oxygen, that is A. So, if we just rearrange it, so we will get A equals 1 by 4 W gamma S minus C gamma B minus F J gamma P. So, this A, this is called the theoretical oxygen demand. Now, further this electron balance, as we know the principle which I discussed here, it says available electrons are conserved during the metabolism. So, what it says is, we can, if you go for this electron balance, so let us assume here this electrons from this substrates are distributed to the biomass and product. So, what we can just rearrange this equation, we divide by W gamma S. If I divide by W gamma S, so this will be 1 equals 4 A divided by W gamma S plus C gamma B divided by W gamma S plus F J gamma P divided by W gamma S. Now, the first term is oxygen, second term is biomass, third term is the product. Now, let us consider the whole electron balance is divided into, or 1 is distributed into 3 parts. So, what will be the maximum possible if I put this equals to 1, maximum possible product if I put this equals to 1. So, if I put this term as a 1, so it becomes C gamma V W gamma S equals 1. So, here C, in place of C we write C max, and if I just rearrange it, so it gives C max equals W gamma S divided by gamma V. Similar, if I consider this term as 1, so this will be F J gamma P upon W gamma S equals 1, and when we are putting 1, then this will be F max. If I rearrange, so you will get F max equals W gamma S divided by J gamma P. Now, before we proceed further, let us practice a few example here. The first thing will be to calculate the degree of reduction. So, for example, if I say you are having ethanol, so if I say you are having ethanol, it means it is C2H5OH. Another, let us say one more example, that is the glucose, it is C6H12O6, and one more compound, let us take methane, CH4. So, let us calculate the degree of reduction for all 3 compounds. We know how to proceed. For the carbon, the balance is +4, hydrogen the balance is +1, oxygen the balance is -2. So, this will be for the carbon it will be 8 plus hydrogen 6 minus oxygen 2 divided how many carbon atom 2. So, this will be 6. If I calculate for the glucose, so this will be for the carbon 24, hydrogen 12, oxygen 12, oxygen minus 12 divided by carbon atom 6. So, this will be 4, and if I calculate for methane, then this will be carbon 4 and hydrogen 4 divided by carbon atom is 1, that equals to the 8. Now, let us compare this, what does it signify for the ethanol and the glucose. So, what it says is, in the case of glucose the value degree of reduction is less, it means it has more potential for oxidation, more oxidation potential. Potential as compared to ethanol. Ethanol is degree of reduction is 6, it means it is somewhat reduced and it has less potential for oxidation. So, in this way we should be able to calculate the degree of reduction once the molecular formula is known to us. Yes. So, before we proceed for this chemical oxygen demand, let us do one more small exercise. So, it says the F max you should be able to calculate using this equation. Now, we know the glucose is converted to ethanol, C6H12 H12O6, this is converted to ethanol, C2H5OH plus CO2. So, let us say stoichiometric coefficient for this ethanol is not known, I am putting the value here A, here I am putting the value B. Now, what will be the A? A will be here compared to F max. So, this A will be equals to W, what is W here? 6, gamma S is degree of reduction of substrate for glucose, what is the value 4 divided by J, what is the value of J? 2 into degree of reduction of product, gamma P is ethanol is 6. So, we are getting the value of A as 2. So, now we know from the 1 mole of glucose 2 mole of ethanols are produced and similarly 2 moles of carbon dioxide are produced. So, in this way this was the simple example, but one should be able to calculate the maximum possible yield or the theoretically what is the value of stoichiometric coefficient of a product or biomass. Now, next further one should be able to calculate this chemical oxygen demand. Let us say if I am going for the oxidation of cell which have this general molecular formula. So, what I have to write? First you have to write the stoichiometry reaction. So, let us write the stoichiometry reaction for this. It says CnHA OB NC. This will require some amount of oxygen, and what will be the product of oxidation will be NCO2 plus C times let us say ammonia NH3 plus water H2O. The stoichiometric coefficient for water is A minus 3C upon 2. And stoichiometric coefficient if I see for oxygen, now this will be for N, this will be 2N for oxygen 0.5 A, then for C this is 1.5 C minus 1.5 C, and for the B, this is the B, so this will be minus B and divided by 2. So, this is the stoichiometric coefficient for oxygen. So, if you know this stoichiometric coefficient of oxygen, so I can directly write what will be the COD, chemical oxygen demand will be the how much oxygen is required, 2N plus 0.5 A minus 1.5 C minus B divided by 2, but its molecular weight of oxygen 32, this much gram, and how much is the amount of substrate which is being oxidized, that is the Cn, it means 12N, its mass will 12N plus 1A plus 16B plus 14C. So, in this way one should be able to calculate the chemical oxygen demand. So, I have put one simple example here. The cell contains 48.9% carbon, 5.2% hydrogen, 24.8% oxygen and 9.46% of nitrogen. So, this is the weight percent. So, what you have to do, if you want to calculate the stoichiometry, you have to calculate their mole percent. So, let us write here carbon, hydrogen, oxygen and nitrogen. So, for carbon the value is, this is the weight percent 48.9, 5.2, this is 24.8 and 9.46. So, what we have to do? We have to divide by its molecular weight, then this will be converted into their moles, respective moles, and if I divide by carbon 12, so this will be approximately 4 moles, hydrogen that will remain same 5.2, this I will divide by 16, I will get 1.55, and for nitrogen I have to divide with 14, so this will be 0.67. So, what is the molecular formula of the cell? It is coming out to be C4H 5.2 O 1.55 and N 0.67. So, one option is this, second option is what we can do, we can normalize, we can make 0.67 to 1, it means we are multiplying with 1.5 to all. So, this will be then 2.3, this will be 7.7 and 4 will be 6. So, another formula we should be able to write, equivalent formula for biomass C6 H 7.7 O 2.3 and N 1. So, we are, as of now we are considering this molecular formula, and based on this one should be able to calculate what will be the say chemical oxygen demand. So, if you want to calculate the chemical oxygen demand, 2 into N, what is N here? N is 6, A, what is A here? A is 7.7, what is B here? B is 2.3, what is C here? C is 1, this is known to us, A, B, C everything is known. If I calculate the chemical oxygen demand for this, so this will come out to be, COD will come out to be C 195 divided by 131, this is 1.48 gram per gram of the cell. So, this is the chemical oxygen demand for this combustion. We will quickly do one more similar exercise where it says, can you calculate COD equivalent for glucose. So, what your first step will be, you have to write the oxidation equation. So, it says for glucose C6H12O6 plus oxidation reaction 6O2, this will convert to 6CO2 plus 6H2O. Now, if I want to calculate the COD, what is the amount of oxygen is required? 6, molecular weight of oxygen is 32 divided by the molecular weight of substrate, that is glucose 180. So, this comes out to be 1.067 gram of oxygen per gram of glucose. So, if I say, can you calculate the dissolved oxygen consumed if glucose concentration was 100 milligram per liter? What was the amount of glucose? If we assume total volume 1 liter, assume total volume as 1 liter. What was the amount of glucose? 100. So, for 1 gram we require 1.067 gram of oxygen. So, for 100 milligram how much oxygen will be required? So, we will be requiring 100 into 1.067, that is equals to 106.7 milligram oxygen per liter. So, I will stop here. In the next lecture we are going to see the stoichiometry of product formation. Thank you so much.